yesterday, good. So yesterday we sort of had a lightning introduction to two-dimensional conformal field theories. And one of the stated advertisements for our interest in 2D CFTs is that they're a great laboratory for understanding holography, and in particular for understanding the AdS3 correspondence. And we learned yesterday that conformal field theories in 2 dimensions have oodles of symmetry. They have an infinite algebra of symmetries as opposed to a finite algebra of conformal symmetries as happens in higher dimensions. And so because of that, one would similarly expect that 3-dimensional theories of gravity in anti-de Sitter space, namely the putative holographic duals of 2-dimensional CFTs, should similarly have tons and tons of symmetries and should, at least in some sense, be much, much simpler than theories of gravity in higher dimensions. And today we're going to understand how that's the case. We'll understand, or at least motivate the connection between 3-dimensional theories of gravity in AdS and 2-dimensional CFTs. And we'll see in some very, very precise sense that any theory of 3-dimensional gravity can be regarded as a 2-dimensional CFT, completely independent of any statements about string theory or any statements about what your particular favorite theory of quantum gravity is. So I think one very useful perspective on the AdS3 CFT2 correspondence, and this might be a slightly controversial perspective, is that it's something that is completely independent of string theory. And that although AdS-CFT originally arose in the context of string theory and stacks of d-branes and n=4 Yang-Mills as a near horizon limit and all of that stuff, there's a sense in which the AdS3 CFT2 correspondence is really a precise laboratory to see how the AdS-CFT correspondence goes well beyond any particular realization of quantum gravity as a string theory. Okay, but let's begin with something a little bit more elementary, just to set the stage. So what is AdS? Well, AdS is, as you all well know from Mukund's lectures last week, the most symmetric solution of general relativity with a negative cosmological constant. And in particular, if you're studying general relativity in 3 dimensions, and you have a negative cosmological constant, which I'll call -1/L², where L is a dimensionful parameter with the units of length, then one way of characterizing AdS is as a hyperboloid embedded in a space of 1 higher dimension. So in particular here, I'm writing the AdS hyperboloid as a hyperboloid embedded in a 4-dimensional space. This is a very useful way of thinking about anti-de Sitter space because it makes the isometry group of anti-de Sitter space completely explicit just by looking at the form of the metric in 2 + 2 dimensions as I have written here. You can automatically see that this hyperboloid has an SO2-2 symmetry, which is the same as SL2R times SL2R. And in particular, I remind you, as we discussed yesterday, this is the same as the group of global conformal transformations of a 2-dimensional conformal field theory in Lorentzian signature. Now, of course, this picture of AdS as an embedding space is okay, but we'd really like to give some coordinates to this space to represent it intrinsically. So this is now a straightforward exercise. So for example, one nice set of coordinates are the coordinates that I'm writing down here, which would be a radial coordinate rho, a time coordinate t, and an angular coordinate phi. And then if you were to just go ahead and figure out what the induced metric is, it's a very easy calculation. You've probably done this calculation or ones very much like it before. you can see that you have a form of the metric that is d rho squared minus cosh squared rho dt squared plus sinh squared rho d phi squared. These are what are known as the global coordinates in anti-de Sitter space, and they provide a very nice picture for how you should think about AdS3 in your head. You should really think about AdS3 as a solid cylinder. Okay. So here, the angular coordinate phi is the spatial coordinate. T runs vertically in this picture. And you should think of AdS3 as a solid cylinder that you get by filling in this T phi cylinder that I've described here. So rho equals infinity is going to be the boundary of the cylinder. And as rho runs from 0 to infinity, you're sort of filling in the cylinder. So the rho coordinate would look something like that. It would fill in the cylinder. We can write this a little bit differently by defining a radial coordinate, which is going to be the radius of the circle. And then this gives us another very nice form for this metric, which again, this is a straightforward exercise in writing down changes of coordinates. So this is another way of writing the global coordinate system in AdS3, where r now is a radial coordinate defined to be the radius of the circle. Okay, so that's a much more conventional name for a radial coordinate. Here, there's a minus sign in front of the dt squared, but we could go to Euclidean signature, and that would just become a plus sign. Now, there's one third coordinate system that I'd like to introduce for AdS3, which would be referred to as the planar or the Poincare coordinates. Unlike the global coordinates, which cover all of AdS3, these only cover a portion of AdS3. And in particular, they cover what's known as the Poincare patch. But the advantage of these coordinates is that they have a planar symmetry. So here, z is a complex coordinate on a plane. So you could write, here I'm writing the metric in Euclidean signature. If we wanted to write z as x plus iy, then dz bar is the usual flat metric on the plane. And this Poincare metric is useful because in this parameterization of AdS, the boundary at r equals infinity is equal to a plane rather than a cylinder. Okay. And this is supposed to remind you of something that we discussed yesterday. So yesterday we discussed two different ways of thinking about two-dimensional CFTs. You could either think about them on a plane or on a cylinder. And here we see that we have different coordinate systems in AdS, one of which has a boundary that looks like a cylinder, and another of which has a boundary that looks like a plane. Okay. So this, it turns out, is not merely a coincidence, but rather signaling something a bit more interesting.
Could I ask you a question about this?
Yes, absolutely.
It looks here like you've moved to Euclidean signature in writing dz bar.
Yeah. So let's write a little Euclidean here, if you want.
I would have thought that in Euclidean signature, the Poincare coordinates cover everything because it's just like the upper half space model for hyperbolic space.
The upper half space model of hyperbolic space misses a point at infinity. But aside from that, you're correct.
Okay, sure.
Good. So just as an exercise, I won't bother doing it explicitly. Find the coordinate transformation. Between these two coordinates. Okay. Just as a hint, in order to find this coordinate transformation, note that I have been very lazy in writing these down, and the radial coordinate that I have defined here in global coordinates is not the same as the radial coordinate that I've defined here. But I'm just not nearly creative enough to think of other names for the radial coordinate aside from r and rho. Good.
You said that like it's similar to the CFT on a plane or a cylinder, but Poincare patch only covers part of it.
Correct.
So then isn't this a problem? Or
well, there's no rule. Okay, so remember that if you have a CFT, you could either, yesterday we talked about CFTs and we talked about them either as being defined on C star, the Riemann sphere, which is an S2, or on a plane, which is the sphere minus a point, or a cylinder, which is a sphere minus 2 points. And so this sort of thing doesn't tend to bother us too much. You just have to be a little careful. And this is related to the question that I think Jonathan asked a minute ago, which is noting that in Euclidean signature, these Poincare coordinates don't actually cover all of Euclidean AdS3, otherwise known as hyperbolic space, but only that minus a point. Okay. So this doesn't bother us too much.
Good. Thanks. Yeah.
Great. Okay. Now, when we study gravity in AdS, we're not, of course, interested only in anti-de Sitter space, right? For the same reason that when we study general relativity, we're not just interested in flat space. When we study gravity in anti-de Sitter space, we're not interested only in anti-de Sitter space. But we still want to restrict our attention to a certain class of geometries. So in particular, when we say we're talking about gravity in anti-de Sitter space, let's be careful about specifying exactly what we mean. So when we say we're studying gravity in anti-de Sitter space, what do we mean? What we mean is that we are studying a particular set of metrics that look like anti-de Sitter space asymptotically. So in particular, what we're going to demand is that we're only going to study a particular class of metrics, namely those that look like anti-de Sitter space, plus terms that are subleading as you take R to infinity. Now, it turns out that you need to be a little careful about what you mean by subleading, okay? So in particular, if you go through the analysis of gravity and anti-de Sitter space carefully, it turns out that the proper definition of what we would mean by an asymptotically AdS geometry is one where we specify precisely how the different components of the metric should fall off at large radius. And it turns out that there's actually more than one possible specification of those fall-offs, and those actually lead to different notions of what you would mean by gravity in anti-de Sitter space. This is the subject of a very beautiful paper by Brown and Hanot, which in some sense is the first paper on the AdS-CFT correspondence. But I'm not going to, for the sake of time and because it's a rather technical analysis, I'm not going to go through their analysis in detail. But I'll simply say that for the purposes of the calculation that I'm doing today, what I mean by subleading in R is literally subleading in R, okay? Namely, that those terms that are subleading in R will fall off as R goes to infinity, okay? So in particular, there'll be things that are, for example, order 1 as R goes to infinity for the Z and Z bar components of the metric. And if you do the analysis in more detail for the other components of the metric, for example, the dz, dr components of the metric need to fall off like 1 over r cubed, if I remember correctly. But in any case, the point is that we need to specify precisely what it means to have an asymptotically AdS metric. And in particular, in this case, what it means is that the metric takes that specified form plus terms that are subleading as R goes to infinity. And in particular, that are constant as R goes to infinity. And given this definition, there are actually 2 different things that we mean by the symmetry structure of anti-de Sitter space. So for example, as we already stated earlier, the symmetry group, that is to say the isometry group of anti-de Sitter space, that's SO2, 2. And what is that? That is the isometry group, which is to say the set of diffeomorphisms that preserve the form of the metric. But, and this is the point that Brown and Hanot articulated very clearly, there is a separate notion of a symmetry group that we could consider, which is the asymptotic symmetry group of asymptotically anti-de Sitter spacetimes, which is the set of diffeomorphisms that preserve this asymptotic structure. That is to say, that preserve the general form of the metric that we have specified for our theory of gravity. Okay. And what Brown and Hanot did is they analyzed the different possible types of fall-offs that we could demand, the types of subleading behaviors you could demand, as well as analyze the different possible asymptotic symmetry groups. So in particular, yes, please.
I was just going to ask, is it the case that for each choice of like subleading terms, there's a different asymptotic symmetry group?
That is true. But what Brown and Hanot did is, and this is actually what I'm going to discuss in a minute, is they discussed that there are further constraints that we need to pose on these symmetry groups. Remember, as we discussed last time, the most important thing is not just the symmetry group, but the charges that generate those symmetries in the phase space of the theory. So what Brown and Hanot did is they constrained the possible choices of boundary conditions by demanding that these charges exist and that they are finite. Okay. So I'll sketch a little bit how they did this calculation very schematically, but roughly speaking, the way that you compute these charges is by varying an action. Okay, these are charges that generate diffeomorphisms. So they're, the corresponding charges are going to be built out of the stress tensor. And so you need to study the stress tensor of this theory, compute the corresponding charges, and demand that they're finite. Okay. And we're going to go ahead and discuss that momentarily. Okay. But first, let's just think a little bit about the sorts of diffeomorphisms that would preserve this asymptotic structure for the metric. So in particular, you could imagine that you have, say, a translation of the z coordinates. Okay, that obviously preserves the form of the metric because z to z plus a constant doesn't do anything to dz, so that preserves the form of the metric. Similarly, you could take z bar to z bar plus a constant. We'll call it epsilon bar. But what would happen if you tried to consider a more general type of diffeomorphism? For example, one where epsilon and epsilon bar are functions of z and z bar. Well, let's, for example, imagine that you took epsilon to be linear in z. Well, then dz would rescale by a constant. So that, at least naively, would not preserve the asymptotic form of the metric, because I've changed the coefficient of r squared dz dz bar. But we've got a radial coordinate there, so you could always compensate that. In particular, you could rescale the radial coordinate at the same time that you're rescaling the z coordinate, and then you would have a member of the asymptotic symmetry group. You'd have a good asymptotic symmetry that preserves this prescribed form for the asymptotic behavior of the metric. So it turns out that, so that means that something like a scale transformation will also be a legitimate member of the asymptotic symmetry group. So in particular, you're going to have something like the following. So if epsilon is linear in z, then you're going to need to rescale r by some amount that's proportional to epsilon prime. And in particular, it turns out that for any holomorphic function of z and anti-holomorphic function epsilon bar, you can always find terms in the diffeomorphism that will arrange themselves in such a way that you'll get a member of the asymptotic symmetry group. So in particular, any pair of functions epsilon of z and epsilon bar of z bar will lead to a member of the asymptotic symmetry group. And I've described in words how this works when epsilon is a constant or linear in Z. And so it's a straightforward exercise and a sort of fun one to check that this very general set of coordinate transformations that I've written here preserve the asymptotic structure of the metric. Okay. So now, here I've written down an explicit form of a diffeomorphism involving a function epsilon of Z. This epsilon of Z is characterizing how the diffeomorphism behaves near the boundary. That is to say, how it acts on the boundary. And in particular, you should remember yesterday how conformal transformations acted on the complex plane, right? Z went to some other holomorphic function of Z, and Z bar went to some other anti-holomorphic function of Z bar. So you can see that diffeomorphisms in the bulk that preserve this asymptotic structure of the metric are generating conformal transformations on the boundary. And in particular, we see we don't just get the rigid conformal group, which was the full set of isometries of AdS, but you now also get the local conformal group, which is the set of asymptotic symmetries of AdS.
Can I ask a question real quick?
Yes, please.
In your exercise there, on that top line, are those bars there, or should that not be bars? Because
on the top line, there is a bar, an epsilon bar double prime of Z bar. Yes. Okay, exercise, show that you need it.
Okay, cool. Good. Thank you.
Right. I mean, this is why Brown and Hanot are smart guys, right? Well, it's not why they are. It is evidence that Brown and Hanot are smart guys. Okay.
This is not holomorphic then, right?
Got my causality reversed there. Yes. What was that?
This is not holomorphic then, right? Because
epsilon is a holomorphic function and epsilon bar is an anti-holomorphic function.
Yeah, but then Z is becoming
in the interior of AdS, everything gets all mixed up. It's only near the boundary.
And the R goes to infinity.
In the R goes to infinity limit that the conformal transformations completely factorize.
I see. Also, is this the only transformation that preserves the asymptotic structure?
Absolutely not. And that's the next thing I was going to say. Because you could always take a diffeomorphism that acts in some non-trivial way in the interior, but does nothing out at the boundary. Okay? So how would you describe that? That would be a diffeomorphism with epsilon equal to 0. So if epsilon and epsilon bar are equal to 0, then all of the leading terms that I've written here are 0, and only the subleading terms are non-zero. Of course, this is an element of the asymptotic symmetry group, but it's something that we regard in the usual way in theories of gravity as a gauge transformation. So in particular, in a theory of gravity, diffeomorphisms are regarded as gauge transformations in the sense that metrics related by them in particular, a metric related by such a diffeomorphism are identified, right? You know, if you've got if you got a sphere, for example, and you do the diffeomorphism that rotates the sphere, then you think of those as the same geometry. They give, you don't think of them as giving distinct describing distinct solutions of general relativity, or for example, giving distinct contributions to a path integral or describing distinct states in a quantum theory. And so the diffeomorphisms with epsilon equal to 0 are gauge symmetries in the usual sense that we think of gauge symmetries in a gauge theory or in a theory of gravity. But diffeomorphisms.
Sorry, I just have a question about the previous point. Sorry if it's disrupting your flow. The previous point where you said that these asymptotic symmetries only factorize into holomorphic times anti-holomorphic out at the boundary. Is there a CFT intuition for that?
I mean, we had countered this a little bit yesterday when we talked about modular invariance, and we noted that modular invariance does not act separately on holomorphic and anti-holomorphic. This is going to come back and haunt us later. I mean, there is an analog of this. I mean, avatars of this show up in CFTs in many different ways, right? The factorization between holomorphic and anti-holomorphic happens at the level of symmetries in CFTs. That is to say, it happens at the level of kinematics in CFTs. It doesn't happen at the level of dynamics, right? All of the non-trivial dynamics in a CFT mixes up left movers and right movers, right? You know, if you only talk about kinematics and symmetries, you would be misled into thinking that left movers never talk to right movers, but you couldn't be wronger if you tried.
Great, that makes a lot of sense, thanks.
Okay, but here is the beautiful observation of Brown and Hanot, right? Which is that diffeomorphisms with epsilon not equal to 0 are not pure gauge. Okay. In particular, the diffeomorphisms with epsilon not equal to 0 generate an algebra of symmetries for the theory. And what is that algebra of symmetries? Well, you know what it is because we worked it out yesterday. The algebra of symmetries is going to be the Witt algebra. But when you implement these as charges acting on the phase space of the theory, it's going to be the Virasoro algebra. Because what do charges do for a living? They give you central extensions of the algebra of symmetries.
Just to be
so
clear,
in particular, they generate a copy of Virasoro times Virasoro acting on the theory. Good question.
Yeah, sorry. Should we be able to see that here, or should we just believe that?
The fact that we have z going to epsilon of z out at the boundary and z bar going to epsilon of z bar out at the boundary means that you could write down the vectors that generate these diffeomorphisms, right? Diffeomorphisms by definition are generated by vectors. So write down those vectors and compute their algebra, okay? You know what that's going to look like, however, because out at r equals to infinity, all of those things that fall off like 1 over r squared don't matter. And so the algebra is just going to be the Witt algebra. Okay. Exercise, compute it. Good. I love that I can give exercises, right? It means that I don't actually have to answer any questions. I wish I could do this on every seminar I gave. Good trick. Okay. Now, how did Brown and Hanot conclude this? They concluded this by computing the charges associated with these things. They computed them explicitly. Okay. So in particular, these charges that generate these were computed explicitly by Brown and Hanot. And indeed, they defined the set of asymptotic symmetry conditions precisely by the condition that you have charges that are non-zero. So for example, you could try and define boundary conditions that blow up more quickly at infinity or something like that, but the corresponding charges that generate them would diverge. Okay. So, you know, the boundary conditions that we're considering here are precisely those for which the charges are finite. Okay. And in particular, you know, spoiler alert, these charges are going to obey the Virasoro algebra with some central charge. And this central charge was computed by Brown and Hanot. Okay. So the resulting central charge well, what could it possibly be? So in order to understand what it could possibly be, let's remember that we're talking about a theory of gravity in AdS. So because it's a theory of gravity, there's Newton's constant, which has dimensions of length. And there's an AdS radius, which has dimensions of 1 over length squared. Okay. Central charges by definition are dimensionless. So that means it's going to be some function of L over G. That is, they have some function of the AdS radius in Planck's units. And indeed, Brown-Hanot showed that it's 3L over 2G. Okay. So this then is the central charge of this theory of gravity. Notice at this point, I've used no CFT, right? This is a theory of gravity, right? With symmetries that are equal to 2 copies of the Virasoro algebra, and with a central charge that's computed in this theory of gravity. Now, the computation of Brown and Hanot is actually rather technical. I don't want to go through it in detail. You can sort of see that the central charge has to take the form of something times L over G. Roughly speaking, the way that you can see that is you remember first that it has to be dimensionless, and then you remember that charges are found by varying an action, right? The action goes like 1 over Newton's constant, because that's the action. The Einstein-Hilbert action is 1 over 16 pi g times root gr. So each charge is going to have a factor of 1 over g. Okay. So if you were to do an analysis, a computation of the Virasoro algebra, what sort of computation would you do? Well, you would look at the variation of one of these charges under one of these asymptotic diffeomorphisms. That's how you get a commutator in an algebra. A commutator in an algebra is something that tells you how one symmetry generator transforms under another symmetry. Okay. And if each one of those symmetries has a factor of 1 over g in it, you can convince yourself that any extra constant term, any extra central charge that would appear also has to be proportional to 1 over g. That's just dimensional analysis. So combining that with the fact that there's only one other dimensionful scale in the system, you can immediately conclude that the central charge must be proportional to the AdS radius in Planck units. That is to say, proportional to L over G. And what Brown and Hanot did from this point of view is compute the overall constant, namely that it's 3/2.
Sorry, when you said commutator, did you mean Poisson brackets or?
So what I mean is Poisson brackets, of course, because I'm talking about a classical theory of gravity. But when we imagine going to a quantum theory, as usual, Poisson brackets are going to become commutators. Okay.
Right, yeah, because if I just computed the commutators, then it would be just Witt algebra, right, here.
The commutators of symmetries, right? I mean, an important point is that commutators of symmetry generators, as diffeomorphisms, for example, are not the same as the commutator of the Poisson bracket of charges acting on a phase space. And that's in addition, and it's also not the same as the commutator of operators acting on the quantum theory, because they can all differ by central terms.
Poisson bracket is the same as the commutator of the charges, right?
No, the Poisson bracket will in general be a central extension.
Right.
So exercise, I suggested last time doing this for the commutator of Galilean boosts and momentum for a particle moving in 1 dimension. Use the Noether procedure to compute the Poisson brackets, to compute the charges that generate a Galilean boost. Okay, and you'll see that its Poisson bracket with P is not 0, it's the mass of the particle. Okay.
Right, thanks, yeah.
Of course, when you quantize the theory, those Poisson brackets will become commutators and you'll pick up a factor of IH bar.
Right.
In the usual way in quantum mechanics. Great.
Where here is it important that gravity is dynamical? Because we could, if we considered like quantum field theory on AdS, we would still have these diffeomorphisms acting.
But you wouldn't be constructing charges out of them by, so you wouldn't have charges, the charges built out of them, well.
Is it that you would only have the global version, not the local version?
Yeah, I think maybe the best way of saying this is that it would be something like a mutilated conformal field theory where you're not allowing the stress tensor to be a dynamical operator in the theory, something like that. But I may be I'm going to talk about, so far I've only discussed general relativity and not adding matter to the bulk theory. We're going to get to that in a little bit. Okay, great. So the result suggests that any theory of gravity in AdS is a CFT. Okay. This is not a proof, but it sure is a strong hint, right? Because it is a theory which has a symmetry group, that is the same symmetry group, namely Virasoro algebra, with some central charge that we can compute. Okay. So I've told you about the symmetry structure of the theory. What about the states? So what are the states in the theory? Well, let's start with the ground state. So the ground state is going to be empty AdS, right? Whose metric we already met before.
Can I interrupt you with a question about symmetries?
Sure.
So presumably when you derive the Brown-Hanot central charge, the action you vary is presumably the Einstein-Hilbert action?
Plus boundary terms.
Plus boundary terms.
And in particular, and could also include matter terms.
And could include matter terms.
But
so when we say, yeah.
But it turns out that the specified fall-off conditions on the metric imply specified fall-off conditions on the matter terms, which imply that they actually aren't going to contribute to these stress tensors. So it turns out that you can compute these charges only by thinking about the Einstein-Hilbert plus boundary term part of the action. Okay. The specification of these boundary terms is a little bit non-subtle, a little bit subtle, because it includes not just the Gibbons-Hawking term, but also what we refer to as counter terms, things that you need in order to get finite answers.
Sure. But maybe my question is, if we, well, no, I mean, it's all good information. But my question is that you said, you know, this analysis implies that any theory of gravity in AdS3 is a CFT, which is certainly something I believe. But if, you know, there are theories of gravity that are not Einstein gravity, higher curvature, Lovelock, whatever your favorite classical theory of gravity is, would you say that this analysis also implies that any theory with those low energy effective field theories is a CFT on the boundary?
Yeah, it turns out that the Brown-Hanot analysis is sort of shockingly general. The way that I think about it is that you can show that any theory of gravity in AdS3 by a field redefinition, this is a little bit off track, by a field redefinition, you can rewrite it as general relativity in 2+1 dimensions. This is a very strange fact about GR in 2+1 dimensions. It's very different from higher dimensions. And so because of that, this analysis would also more or less go through in any theory of gravity, including higher curvature, Lovelock, whatever. Okay. That's actually a rather subtle point, though. It's quite different from gravity in higher dimensions. I'm going to talk in a little bit about how to think about GR in 2+1, but maybe we'll get there when we get there.
Sorry, just a follow-up on that. Is there a so you're saying any theory with higher derivative can be field redefined to Einstein gravity?
Yes.
So
that's
is this invariance also apparent in CFT, or is it not there?
I don't really know how to think about that in a CFT language because we use different variables in the CFT language. Let me think about that and see if I can come up with a better answer, but I think no is the answer I'll give.
Okay, thanks.
Can I also ask a question?
Okay, but every question you ask is preventing you from deriving the entropy of a black hole.
Okay, maybe I'll wait then.
No, I'm sorry.
I'm just a little confused because we started off with classical gravity and now you're saying that it's a CFT and we're talking about states. So are we doing some kind of canonical quantization here by promoting Poisson brackets to commutators?
Right now, I'm just trying to analyze the symmetry structure of gravity in AdS, and I'm just following my nose by demanding that charges in the classical theory are promoted to operators in the quantum theory. The same way that we did in the discussion of CFT. We started with a classical set of symmetry generators, and then we demanded that they turn into operators acting on a Hilbert space of the theory in a quantum theory, doing the exact same thing. It might be useful, and this might be where you were getting at, to do a bit of dimensional analysis. Remember that I am using units where the speed of light in h bar equal to 1. But if I were to restore my factors of h bar in the bulk, this central charge would go like 1 over h bar. So the classical limit of the bulk theory is the large central charge limit in a conformal field theory. This will come back to haunt us later.
All I meant was if we're trying to do quantum gravity,
well,
it has nothing to do with the way that we quantize regular quantum mechanical systems.
Quantum gravity is a mystery, of course. This is a sort of ground up approach where I'm just starting by analyzing the symmetry structure. So, right, I'm starting with a sort of, if you like, semi-classical analysis, where I start by analyzing the symmetries. I demand they are promoted to operators acting on the Hilbert space of the theory. I'm now going to analyze the classical solutions and demand that they correspond to states in the quantum theory. And then we'll discuss exactly what will happen when you go from this classical theory to a quantum theory.
Okay, thank you.
Great, thanks.
Sorry, can I just ask one more quick question? I was a bit confused about the comment you made earlier about when having the bulk fields, they don't contribute to the stress tensor.
Mm-hmm. So that's a computation. That's non-trivial. That's like not supposed to be obvious.
Okay, yeah. And so does this mean that even if you put bulk matter fields, they don't affect the central charge of the CFT on the boundary? Or
effectively, what happens is the way that you think about it in the bulk is that whenever you have bulk fields, they're going to renormalize coupling constant. And in particular, they're going to renormalize Newton's constant. And so the effect of these bulk fields on this central charge and on this calculation is entirely captured in the renormalization of Newton's constant. Or I should say better, because Newton's constant is dimensionful and the AdS radius is dimensionful, the entire effect of bulk fields is going to be captured by a renormalization of the dimensionless ratio L over G.
Okay, interesting, thanks.
Yeah. Good questions. Okay, but I want to derive black hole entropy, and it's not actually going to take me very long. So let's go ahead and do that. First, I need to tell you about the other states in the theory. It turns out that, well, I don't want to say it too strongly, but there is only one other kind of state in the theory. That's actually a lie. But at least in pure gravity, there's only one other simple sort of state that you can construct in this theory, which is known as the BTZ black hole. For Bagnatos, Teitelbaum, and Zanelli, it was actually discovered after Brown and Hanot did their analysis. And in fact, the metric of the BTZ black hole is almost identical to the metric that I wrote down above. In particular, all I do is I modify those warp factors by changing the L squared parameter to a new parameter with dimension of length, which you can immediately see here is going to be the horizon radius of this black hole. And you can compute it in terms of the mass of the black hole. And in particular, if I denote by E the mass of the black hole, then the radius is proportional to the square root of the mass of the black hole. So in particular, when I say dimensionless mass of the black hole, remember that mass has units of 1 over length. So I'm going to rescale by a factor of the AdS radius to get something dimensionless. In the CFT language, here we want to remember that, again, our boundary is going to be a cylinder parameterized by T and phi out at large radius. And so what is this dimensionless mass going to be? Well, it's the mass, or that is to say the energy conjugate to d by dt. Okay, otherwise known as the generator of time translations on the cylinder, otherwise known as the eigenvalue of L0 plus L0 bar in the CFT language. What we would call scaling dimension in the language of the CFT on a plane, or what you would call the energy in the language of the CFT on the cylinder. So in particular, we can see that empty AdS, let's just compare these two expressions. So empty AdS is, so these two metrics are the same if you let R plus squared be minus L squared. Okay. And what is R plus squared? Well, let's just use this formula over here. That's 8GL times E, which is to say E is minus L over 8G. Or if we plug in our formula for the central charge up here, minus C over 12. Okay. What's minus C over 12? We encountered that last lecture. Minus C over 12 is the energy of the ground state of a CFT on a cylinder. Okay. So this is just the Casimir energy of a CFT on a cylinder. And that deserves an exclamation point or two. Okay. Right. So we've already found some interesting and non-trivial match between conformal field theory in 2 dimensions and AdS3 gravity. Namely, the energy of the ground state is related to the central charge in the Virasoro algebra in exactly the same way that it has to be in a 2-dimensional conformal field theory. Okay, we can go a lot farther.
Sorry, why did we have to put in a black hole to see that?
Well, you didn't actually have to put in a black hole to see this. Another way of doing this calculation would have been to just write down the charges that generate time translation and compute their eigenvalue on AdS.
Okay.
But I didn't do that because I'm lazy. Instead, I just compared it to the black hole, right? Because that's a much faster way of doing it.
Okay.
Good question.
Do you mean E is the eigenvalue of L0 plus L0 bar minus C over 12 though?
Well, I have to tell you whether I'm talking, it's L0 plus L0 bar on the plane, which is equal to L0 plus L0 bar minus C over 12 on the cylinder.
Okay. Right, okay. Yes.
You know, we did a kind of lightning discussion of CFT yesterday where I didn't go through that calculation in detail, but it's a good one to do. If you've seen the Schwarzian derivative and stuff like that, that's how one does the calculation. Good.
Also, this is only generator of time translations at infinity, right? Not in the bulk. Yes.
Well, as you can see, I don't know what it, okay. Diffeomorphism invariance means that I only know what a time translation means out at infinity, right? States are geometries, you know, I don't know what a generator of time translation in the bulk means. That has no definition, except with respect to some asymptotic boundary condition. Like if you don't, this is why it's so important when thinking about theories of gravity to be careful about your boundary conditions. Until you decide on what your boundary conditions are, I don't know what energy means because I don't know what time translation means. I can only mean it with respect to a certain set of asymptotic boundary conditions.
Yes, thanks.
Good. Great. So empty AdS is identified as a vacuum state in a CFT with energy minus C over 12. And a black hole is identified with some other state or set of states in a CFT with an energy bigger than 0. Because if E is equal to 0, the horizon shrinks to 0 size. So there's a gap in the spectrum of gravity in AdS, a gap of size C over 12. Now, the black hole entropy, what is that? It's A over 4G. That's the Bekenstein-Hawking entropy. So let's write that down. That's 2 pi r plus the area, that is to say the length of the circle at the horizon, divided by 4G. So what is that? Just plugging in our formula for r plus in terms of the energy, 2 pi times the square root, pulling that factor of 4G inside the square root, L over 2G times E. Or remembering that the central charge is 3L over 2G, C over 3 times E. Okay. Where did we meet this before? We met it yesterday. This is Cardy's formula. So Cardy's formula for the asymptotic density of states of a 2D CFT on a circle at high energy is the Bekenstein-Hawking formula for black hole entropy. And this provides a interpretation of Bekenstein-Hawking entropy as a log of a density of states, completely independent of string theory. Okay. So this is a microscopic derivation of black hole entropy completely independent of string theory. Or at least I should say apparently independent of string theory. There's some secret subtleties here that I haven't discussed that make that story a little bit more complicated. In particular, I don't want to dwell on it in too much detail, but one of the things that's slightly confusing about this derivation of black hole entropy is that although Cardy's formula agrees with the Bekenstein-Hawking formula, they have different regimes of validity. In particular, Cardy's formula is valid in a fixed CFT at large energy, whereas the Bekenstein-Hawking formula is valid in a theory with central charge large, but with energy of order the central charge. You can, straightforward exercise. So exercise, compare the regimes of validity. Of the Cardy formula versus the Bekenstein-Hawking formula. And you'll find that actually they're slightly different. They overlap, but they're slightly different. Okay. And indeed, so this observation that Cardy's formula is the Bekenstein-Hawking formula was made in a paper of Strominger in 1997, within 1 month of Maldasena's first paper on AdS-CFT. In a sense, it's a completely different perspective on AdS-CFT. But even at the time, Strominger mentioned in his paper that the apparent regimes of validity are different and explained this in terms of specific string theory realizations of AdS3 CFT2.
Can I ask a question? Oh, okay.
Thanks. Does the BTZ black hole also undergo a Hawking-Page transition?
I'm going to talk about that.
Oh, okay.
Right now. Yeah. Good. Other questions first, though?
Yeah, just about this point that this is independent of string theory. In deriving the Cardy formula, you use that you really have a local unitary conformal field theory.
Yes.
Does that, and to me, a large part of that is the locality of the CFT. And
yeah,
has what we've seen so far?
Yeah, so locality is something that one can derive and understand in a theory of gravity, where one defines operators by, you take bulk operators, you pull them out to the boundary and use those to define boundary operators. There are some subtleties here because one can only do that for fields that are perturbative in AdS. That is to say, with dimension, in this language, with energy or dimension much less than the central charge. Exactly how that works for heavy operators is something that is a little mysterious from the bulk gravity point of view. So I won't say that this is a mathematically rigorous proof, but I would say that it is, by the standard of physics, a pretty good derivation of the microscopic black hole entropy from a statistical physics point of view.
I guess the question is, how far does showing that the bulk gravity theory naturally has this Virasoro algebra action, how close does that get you to showing that it should be identified with a conformal field theory?
Well, I mean, as we discussed yesterday and earlier in this class, a CFT is a hell of a lot more than just local Virasoro symmetry. Yeah. There's also global stuff like modular invariance. Okay. Indeed, as we'll discuss maybe today or more likely next time, there is a relationship between black hole entropy and modular invariance. That is true not just at the level of Cardy's formula, but true of the geometry as well. Okay. But let me table that for now.
Sure.
Can I ask a question?
Yes.
So you said nothing about the structure of the CFT on the boundary yet, except the central charge. So are we to take this equivalence of Cardy and Bekenstein-Hawking as saying that we only restricted those CFTs where the Cardy formula is still valid or something?
Let me get to that. That's exactly what I wanted to try and discuss. Okay, good. Okay. So let's try and be a little bit more careful in our discussion of what AdS3 gravity look like. And in particular, I don't want to just talk about general relativity. I want to talk about general theory of gravity. General relativity plus stuff. Okay? So roughly, AdS3 is like a box of some size. And in particular, it's a box of size L with reflecting boundary conditions. So in particular, you should think of, here I'm taking now a top-down view of the spatial slice of AdS. It's a cylinder, so the spatial slice is a disk. Okay. Here, the boundary of the disk is this circle. So if you have states at low energy, so energy that is small, then you're just going to have a bunch of perturbative particles bouncing around, built out of whatever quantum fields, for example, are present in your theory of gravity and AdS at low energy. And when will this perturbative picture be valid? This will be valid when the energy is small compared to the AdS radius divided by Newton's constant, right? That's just because the strength, G controls the strength of gravitational interactions. So you've got perturbative stuff when, in the CFT language, the energy of your state is much less than the central charge. So CFT states with energy much less than the central charge describe perturbative stuff in AdS. But if you crank up the energy to be larger than or of order the AdS radius, then all of that stuff is going to collapse into a black hole, right? That's just a property of gravity in a box. If you take gravity in a box, you start dumping energy in, and it's going to collapse into a black hole. So that means that you're going to have black holes when delta is larger or than of order the central charge. Okay. So roughly speaking, you expect that that CFT states with dimension less than the central charge describe perturbative stuff, bigger than the central charge describe black holes. And finally, of course, because physics in a box is discrete, if you take any quantum theory in a system of finite size, then the spectrum is going to be discrete. And so we expect in the full quantum theory, the spectrum to be discrete.
Maybe I missed this, but what was the jump from G times E to the scaling dimension of the operator?
I am just using this formula. So E is, I remind you, L0 plus L0 bar. So because of that, I sometimes call it delta if I am thinking about it in terms of a CFT on a plane, right? So E is the scaling dimension. Right? So I call it E when I'm thinking about energy of the CFT on a circle, or delta if I'm talking about the scaling dimension of operators on a plane. Okay. Good. Now, in particular, one interesting feature of black holes in anti-de Sitter space, as opposed to black holes in flat space, is that because AdS space is like a box with reflecting boundary conditions, it's possible for a black hole to be stable, right? In flat space, a black hole is always going to radiate away due to Hawking radiation, all of its energy. So every black hole is unstable. And that's, that is reflected in the fact that if you were to compute the entropy of a black hole in flat space, and from that compute a free energy or compute a specific heat, then you would find that the specific heat of such a black hole would be negative, So just as an exercise, compute the Hawking temperature of BTZ. How do you do that? You do it by going to Euclidean signature and demanding that the Euclidean solution be smooth, which says that T Euclidean must be periodic so that you're at finite temperature. And show that the specific heat of the black hole is positive, unlike black holes in flat space. So what does that mean? What that means is that black holes in AdS, and in particular, the BTZ black hole in AdS3, is stable. And so here, when you think about the quantum theory and you think about what a CFT state is, you don't actually think about it as being exactly a black hole, but you think about it as being a black hole in equilibrium with its Hawking radiation. Or more specifically, you think about it as a microstate of the theory, which, when properly coarse-grained, is a black hole in equilibrium with its Hawking radiation. Good. I'll mention one more interesting feature of gravity in AdS, which is very different from gravity in higher dimensions, which is that it turns out that Einstein gravity in AdS3 has no local degrees of freedom. That is to say, there are no propagating gravitons in three-dimensional general relativity, as opposed to the 2 local degrees of freedom for general relativity in 4 dimensions. Okay. And in particular, Einstein's equation, which says that R mu nu is proportional to the metric, completely fixes the Riemann tensor so that every solution of, let us call it pure general relativity, that is to say general relativity with no matter present, is locally AdS. Okay. So it's actually not hard to convince yourself of this fact. I'll assign it to you as an exercise. So check this by showing that R mu nu and R mu nu rho sigma have the same number of degrees of freedom in 3 dimensions. Remember, in 4 dimensions, the Riemann tensor has 20 degrees of freedom and the Ricci tensor has 10 degrees of freedom. So 20 is bigger than 10, which is one reason why there are solutions of general relativity that are not just locally flat space. In 3 dimensions, however, this is not the case. So you might think that 3-dimensional gravity, 3-dimensional general relativity is a completely trivial theory. But we just found a black hole solution of the theory. So what the hell is going on? Okay. So it turns out that there are still non-trivial solutions of the form AdS3 mod gamma, where when I mod by gamma, what am I doing? I'm identifying points in AdS with one another. So I'm taking a quotient of AdS by some group, gamma, which is a subgroup of the symmetry group of AdS, SO2, 2. And in fact, it's a highly non-trivial mathematical theorem that every solution of general relativity in 3 dimensions is a quotient of AdS by some subgroup of the isometry group. Okay.
So is that?
Go ahead.
Yes.
So is that statement the same as just saying you're identifying points along killing vectors?
Yes. However, you could always do identifications along multiple killing vectors that do not commute with one another. So very highly non-trivial things can happen. The simplest case is one where you just quotient by a translation along a single killing vector. Okay. And so as an exercise, show that BTZ is AdS3, that is to say global AdS3 mod Z. Okay. I'll give you a hint. Let's look at the metric of BTZ. Notice that phi is periodically identified, as it always is, but it doesn't have to be, right? In global AdS3, if you look up here, phi needs to be periodically identified, otherwise you've got a conical singularity at r equals 0. On the BTZ geometry, however, phi does not need to be periodically identified because it doesn't shrink to 0 at the horizon. It stays finite. So what's the periodic identification that defines the BTZ black hole? It's the one that identifies phi with phi plus 2 pi. So hint, phi is periodically identified with period 2 pi. Good. Now, of course, pure gravity is a very simple theory, a relatively simple theory, where every solution is locally trivial, locally AdS. But if you add matter, of course, solutions of the Einstein equation plus matter are not, in general, just going to be locally AdS. So in particular, pure gravity, that is to say just general relativity, is more or less a topological theory. Whereas impure gravity, gravity coupled to matter, is not. And in fact, there is a very famous and classical result, which is that at the level of perturbative general relativity in 2 + 1 dimensions, that it can be rewritten as a Chern-Simons theory. And what is the gauge group of that Chern-Simons theory? Well, it's the isometry group. So AdS3 gravity is a theory where there's a very sharp analogy between gravity and gauge theory. So much sharper than in higher dimensions. In particular, pure general relativity is literally a gauge theory, at least at the perturbative level. At the non-perturbative level, however, things are much more subtle. Right? Because, for example, in a Chern-Simons theory, usually one considers a Chern-Simons theory where you study the space of flat connections on manifolds of fixed topology. But in a theory of gravity, of course, we allow the topology of space-time to fluctuate in addition to the metric of space-time. For example, black holes are solutions where the topology of space-time in Euclidean signature differs from that of flat space, right? By definition, okay? Because the Euclidean time circle is contractible for a Euclidean black hole, and it's not contractible in flat space, right? That's the definition of a black hole. One definition of a black hole is that it is a solution that in Euclidean signature has a contractible time circle. That's what it means for a black hole to have a temperature. Indeed, that's what it means to have a horizon. The time circle is contractible at the horizon. Good. One important fact, though, yes.
5 minutes.
Okay, perfect. There's one important fact, though, that is worth mentioning, however, which is that even though there are no local degrees of freedom, that is to say, no local gravitons, there are still what we would call boundary gravitons, or if we were to use the language of condensed matter physics, what we might call edge modes, associated to these diffeomorphisms that don't vanish at the boundary. Right. So remember, what is it that I mean when I say that there are no local degrees of freedom in general relativity? What I mean is that any two different solutions of general relativity can be related by a diffeomorphism. And so if you treat diffeomorphisms as gauge symmetries, these don't give you new solutions or new degrees of freedom. But we started out this discussion by talking about which diffeomorphisms in gravity are regarded as pure gauge and which ones are not. And in particular, the diffeomorphisms that don't vanish at infinity are not regarded as pure gauge. They're regarded as defining new states in the theory. Okay. So what does that mean? That means that you could take empty AdS and you could do a change of coordinates. And if that change of coordinates does not vanish at the infinity, then that new metric is regarded as a different configuration of your gravitational theory. It's the same geometry, right? Because all I've done is a change of coordinates. But because I did a change of coordinates that does not vanish at infinity, it gives a new contribution to the theory. So it gives new states in the theory. And what do you call the states that come from changes of the metric? Well, you call them gravitons. Okay. So this theory does have gravitons, but it does not have local gravitons. These, because they only arise in the presence of a boundary, these are things that we refer to as boundary gravitons. They are genuine states in the theory, and they roughly correspond to the edge modes that you might get in some sort of quantum Hall system or any other sort of theory that would be described by a Chern-Simons theory at low energy. And what are they in the language of conformal field theory? Well, they're descendant states. Because what are descendant states? Descendant states are states that you get when you act with a bunch of Virasoro generators on the vacuum. Okay? And what are the Virasoro generators? They're the generators of the diffeomorphisms that act on the boundary. So in particular, we saw last time that the states in a two-dimensional conformal field theory can be divided into different categories. You can divide them into primary states and descendant states. So primary states, then, correspond to sort of what you might call a genuine particles or black holes that live in the interior of anti-de Sitter space. Whereas descendant states just correspond to these things dressed with some set of boundary gravitons. Okay. So in particular, let me just end with a picture of the spectrum of gravity in AdS. So here I'm going to draw a picture The vertical axis is going to be energy. The horizontal axis is going to be spin. Okay. So this energy in the CFT language is L0 plus L0 bar. Spin is L0 minus L0 bar. Now, I only wrote down the BTZ black hole without spin, but there's a rotating version of the BTZ black hole, just like there is for the Kerr black hole in higher dimensions. So just as with the Kerr black hole, the energy must be greater than the spin. Okay, it must be greater than the square of the spin for the Kerr black hole. Turns out to be greater than the spin for the BTZ black hole. And so your black hole states are going to live in this upper triangular region. So these are black holes. Then you're going to have a vacuum state with 0 spin and energy minus C/12. And then you're going to have a bunch of perturbative states. And these perturbative states will include boundary gravitons, but could also include other stuff, okay, if you have other fields in addition to just the metric. And there is a unitarity bound, which says that all of the states in the theory have to live above those dotted lines that I have drawn here. Okay. And this is the general picture for what the spectrum of gravity in AdS looks like. Okay. You've got a bunch of discrete states. So here, I'm talking about classical gravity. So you've got a bunch of discrete states which correspond to perturbative particles in AdS. They're discrete because AdS is like a box. And so wave functions get quantized and have their energies quantized in a box. And then you have a continuum of states that are described by these black holes. So I'm going to stop here, see if there are any questions. I apologize, I only have about 5 minutes for questions since I need to go pick up my kids early from school today.
All right, thanks, Alex. Let's have some questions. Yep. Quick.
Maybe. Oh, go ahead.
Sorry, go ahead.
I have a question about these boundary gravitons. Could I think of this as a renormalization effect? By which I mean, like, okay, the geometry is always the same, even when I do these diffeomorphisms that are asymptotic symmetries. But because I've fixed some conformal structure on the boundary in order to fix some holographic correspondence, once I've fixed that boundary metric, these asymptotic symmetries do something non-trivial to the geometry.
Yeah, I mean, we could always, so for example, if you look in the Brown-Hanot paper, they discovered that there are in fact another completely consistent set of boundary conditions you could impose that are much stronger. And in particular, with those boundary conditions, there are no asymptotic symmetries, there's no Virasoro symmetry, and in fact, there are no states with mass whatsoever. Okay, so these boundary conditions are perfectly consistent, but they're so strong that basically they don't allow you to have a theory with any non-trivial content. Like black holes, for example, are not kosher with these boundary conditions because the fall-off conditions forbid the BTZ black hole. To me, I think of these boundary gravitons as the analog of edge modes in a quantum Hall system, but you know, they're perfectly other legitimate ways of thinking about them. Great. Any other questions?
Right. Hope that this is a quick question. So when you say, you know, there's primary states and dissident states, and how do you distinguish one that doesn't have that's not dressed with a boundary graviton with one that is? Because
remember,
they're just related by
definition,
gauge transformation.
Well, they're related by a non-gauge transformation. They're related by a diffeomorphism that is not regarded as pure gauge. That is to say, they are related. So a primary state is a state that is annihilated by the LNs, where n is positive. Okay, I've defined for you the LNs as charges acting on the phase space of the theory, right? They're integrals of the stress tensor. So these are going to be promoted to quantum operators acting on the Hilbert space of the theory and a quantization of the theory. So find yourself a state. Okay, here, I mean, this is actually a good exercise. Quantize a free scalar field in AdS, okay? And organize the states into representations of SO2, 2. That's pretty easy. That's basically the standard thing you do when you quantize a scalar field. But then do it in terms of the Virasoro algebra. That is something you only do when you add gravity into the picture. Okay. That's harder to, that's a more tricky calculation. It can be done at the level, it can be done perturbatively. Yeah.
Okay, but when you actually do act this non-gauge transformation at the boundary, does it change the energy of the state?
Absolutely, right?
Oh, I
because
see.
the
Okay.
whole point, remember the point of these, so Ln does not commute with L0, right?
I see.
So L0 is energy. So these things have higher energy, right? They carry energy. That's what it means for these charges to not be non-zero.
All right, that makes sense. Makes sense.
Right, so it's real. I mean, it's if you're used to thinking about gravity, you usually think that two metrics related by a coordinate transformation, you don't even think of them as different things, right? You think of them as the same thing, but that's just not how gravity works in AdS, at least not in AdS3. In AdS3, changes of coordinates that act on the boundary give you new solutions of the theory, new contribution to the theory with different energy, right? L-1 acting on some state has an energy that's 1 unit higher in these AdS units.
Okay, then it is somehow different from in flat space where these are soft here because somehow there's a spontaneous gauge.
This is not, so soft modes, by definition, the definition of a soft mode is one that does not change the energy. Here,
but it's the same story.
It's the same story, right? So exercise, take the flat space limit of this, and then these hard modes become soft modes. Okay. So indeed, the two copies of the Virasoro algebra that are the asymptotic symmetry group of AdS3 gravity, if you take the L goes to infinity limit to get flat space, you get a contraction of that algebra. And what does that algebra contract to? It's called BMS3.
I see. Okay.
Which is the structure of soft, the structure that governs the soft modes of asymptotically flat gravity. Now this is something that always confuses me about about papers people write about this. There's no dimensionful constant aside from Newton's constant, okay? So that means there's no central charge that appears unless you put in some other energy scale, okay? So there's, it's a very different story where any central charge that you get out of a flat space limit would be defined relative to some additional cutoff scale. Now, usually when you study soft modes, you put in a cutoff scale and you define soft to be energy small compared to that scale. So I think that's, but it's on a much different footing, yeah. So these are very much like the soft modes in flat space, except they're hard, right? They have energy.
Okay.
Alex, do you have time for one more question? Or?
I have time for one more question.
Jonathan?
Yeah, so I was curious, has the entanglement entropy been studied for these perturbative states and like how the boundary gravitons contribute?
This is, as I've written it, okay. Well, there's many things you could mean by this. As I've written it, it's a pure state, right? I wrote down a state. There's one of them, okay? You could count the number of boundary gravitons. Okay, exercise. Show that the density of boundary gravitons, this is a good exercise, as a function of energy, grows like that of a CFT with central charge 1. Okay. Exercise 2. Use this to explain the existence of rational CFTs. That is to say, CFTs with central charge less than 1. And in particular, have tons of null states. Okay. Roughly speaking, a rational theory is one where the number of descendants of the vacuum violates Cardy's formula. So which means there have to be rules of null states in the theory. Okay. Good. But one thing you'll notice is that the number of boundary gravitons is vastly smaller than what would be required by semi-classical Bekenstein-Hawking entropy. So for example, if you were to try and think of these boundary gravitons as the analog of soft modes, use them to explain black hole entropy, this would fail in AdS3. When people try and explain black hole entropy using soft modes, they're talking about something much more subtle. They're talking about soft modes that exist, that are built out of, well, there's also soft modes near the horizon of a black hole. And then you need to think about the information that such soft modes could carry. At least in the naive AdS3 version of this, that's not the way things work. But when people talk about black hole entropy from soft modes, that is not what they're talking about by and large, right? They're talking about, among other things, soft modes that build up at the horizon of the black hole, not out at infinity.
Right.
Good. All right. I apologize that I have to go, but more tomorrow.
Okay. Thanks a lot, Alex.
Thank you.
Thank Alex again.